Hi everyone, I am Saad Himmi, master student in robotics at ETH Zurich, and I will present our work, MS-EVS, Multispectral Event-Based Vision for Deep Learning-Based Face Detection. Where is Waldo? And how many people are in this image? These are not easy to answer, but I'm sure you would be more comfortable using the colored images. Color is important for humans to detect or recognize objects. Even though our brain is very good at detecting faces, it can be hard to detect faces in the white like here. Now, imagine if your input looks like this. Event-based cameras, or EVS, are a new type of sensors generating very different data from regular images. In regular images, or APS, all pixels take an intensity value depending on the amount of light it captured during the exposure time, in a synchronous manner. For event cameras, each pixel is independent and outputs an event or a spike anytime it experiences an increase or decrease in intensity. This property results in many advantages as low latency or low power, but the data looks different and researchers have to develop new algorithms. Currently, almost all commercially available event cameras are monochromatic only, so grayscale in a way. In our paper, we focus on exploring what color and infrared data could bring to event-based vision. We choose face detection as an example task, but our approach could generalize to other computer vision applications. In our paper, we introduce the concept of multispectral events and propose a one-on-one comparison of APS and EVS over multiple bands. To do this, we share with the community the first large-scale bimodal multispectral dataset with frame-based and event-based data. If we simplify a bit, a pixel intensity is given by this equation. The light received by the sensor is integrated over all wavelengths to form the grayscale value we see in regular images. For event cameras, the principle is the same, but we only see events when there is a change in intensity. Therefore, nothing holds us from capturing events in arbitrary spectral bands. For example, if we put a high-pass filter in front of an event camera, the pixel intensity becomes this. If the scene is also illuminated with infrared light and our object is reflective enough, it will be visible, and therefore it can generate events, and in this case, infrared events. In our work, we used RetinaFace, a state-of-the-art face detection neural network. For us, it was important that we use the same model and number of parameters to thoroughly compare APS and EVS performance on the different multispectral data. Actually, we tried to reduce as much as possible the differences between our APS and EVS experiments, so that the only difference is the sensor, so APS or EVS, and the input spectrum, so like color, grayscale, or infrared. However, there is no large-scale event-based dataset for face detection. To solve this, we propose the MS-EVS dataset. It is a combination of 4 smaller datasets that each serve their own purpose. On the first hand, N-MobiFace and N-YoutubeFaces are online datasets that we converted into event-based data. The main advantage of this method is to quickly get a large-scale face detection dataset with reliable labels. These datasets only have RGB data, but contain thousands of video, enough to pre-train our face detection multispectral models. On the second hand, N-SpectralFace and RealSpectralFace are datasets that we captured and labeled ourselves. In order to explore the benefits of multispectral bands for event-based data, we needed multispectral data. So we used a beam splitter setup to capture the same scenes using a multispectral camera and an infrared camera. This way, we're able to anticipate how multispectral events would look like, and we can fine-tune our phase detector models accordingly. For your information, these are the exact setups we used to capture N-SpectralFace and RealSpectralFace. Note that RealSpectralFace contains a lot less data and only 2 bands, grayscale and infrared. However, it consists of real events, so we can verify our conclusions also generalized to real data. Now that we have datasets, let's talk about how we can evaluate these multispectral events. First, we carried the single channel experiment. where we simply fine-tune our model on a single of the 10 multispectral bands of N-SpectralFace. The goal was to identify if some channels were performing better than others and compare APS and EVS performance. So now let's dive into the results. Here we can see the mean average precision of all the different single channel models we trained. From left to right, we can see the 8 bands of the multispectral camera, the grayscale channel here, and the infrared channel from the second camera. In blue, it's the APS models, and in red, it's the event-based models. Of course, the higher the metric, the better. The first thing we can notice is that the APS models perform better than the EVS ones. Interestingly, for both sensing modalities, the performance is quite constant across all visible channels. This lack of variation suggests that the contrast is relatively similar in all visible bands. On the other hand, we see a clear drop in performance for the infrared band, for both APS and EVS. Let's keep that in mind. In this first experiment, we kept the monochromatic logic of grayscale data. However, the advantage of color data is the new contrast that emerges from combining different bands. Therefore, we conducted a multi-channel experiment where we fine-tune our models on combination of the different bands. We focused on answering two main questions, always for both APS and EVS. What happens when we increase the number of channels in the input, and does infrared has any particular effect on phase detection? We selected the different input combinations accordingly. Each visible-only input is paired with a model that includes infrared data. The legend is the same as before. About the number of channels, for APS, the performance is again constant. On the other hand, the effect on EVS data is very clear. There is a linear improvement with the number of channels at first, then a plateau. We can notice that multispectral events are not much behind multispectral images anymore for phase detection. Also very interesting, infrared always improves APS and EVS. This is even more surprising given that the infrared band was the least performing one in the single channel experiment. Now, one could claim that our results are trivial, and if you use more channels, your data carries more information, which means a better detection, right? Yeah, this is true, but our most important result is that EVS uses more effectively the multispectral data. We've seen that APS color shows no advantage over grayscale images, but EVS color does. On the other hand, APS with infrared shows 1 to 3% improvement, while events with infrared improve twice as much. In this table, we show the gain in performance of the different multispectral combination against their best single channel. Just from the colors, it is obvious that EVS really benefits from multispectral data, especially for the strict AP75 metric with a maximum of 9% improvement. Why is that? We think that it's because regular images are dense and structured, while event-based data is not. So it benefits more from the redundancy in the channels. It could also be because EVS captures contours or edges, which are known to better benefit from color. In conclusion, we tried to carry the first explorative study on multispectral event-based data. We built the MS-EVS dataset, which is composed of 2 large-scale phase detection datasets with synchronized RGB APS and EVS data, thanks to simulation. It also has the first multispectral EVS phase detection dataset for fine-tuning, with 10 different multispectral bands. We also carried the first fair learning-based comparison between APS and EVS modalities, using the same model and data for our experiment. From these experiments, we showed that multispectral events have a big potential. The sensing modality seems to benefit better from combination of channels within the visible and show an additional improvement when we add extra visible data, like the infrared. For more information, have a look at our paper, and thank you for listening.